para presentarme, mi nombre es Luis Garcés, yo soy profesor en el Instituto Tecnológico y también aquí de la Universidad de Costa Rica. Yo soy actualmente estudiante de doctorado en Francia, en la Escuela de Minas, Universidad Federal de Toulouse. Yo soy egresado aquí de la Escuela de Ingeniería Industrial hace unos 15 años, entonces aprovechando, digamos, con el doctorado, yo hago, digamos, un doctorado tipo sándwich, 6 meses aquí, 6 meses en Francia. Y los 6 meses que estoy aquí, digamos, nos visitan los profesores de Francia, el tutor. Entonces aprovechamos para hacer la siguiente actividad. Entonces vamos a hablar tener la charla con el Dr. Paul Pitiot. Él es profesor asociado de la Escuela de Minas, es uno de los tutores míos, él es experto en la parte de algoritmos y en la parte de optimización. Él es ingeniero mecánico, tiene su doctorado en sistemas industriales y también tiene un postdoctorado en sistemas industriales y se ha especializado en lo que es la parte de optimización con algoritmos evolucionarios, en lo que es configuración concurrente, producto, proceso. Entonces ya vamos a ver qué es eso. Tiene que ver un poquito con la parte de investigación de operaciones, lo que son algoritmos genéticos, entonces tiene que ver un poquito con esa temática. Entonces realmente lo que hacemos es configurar un producto y después hacemos lo tradicional, programar el proceso productivo. En este caso lo que hacemos es definir, bueno, qué es lo que voy a producir yo y al final, digamos, configurar al mismo tiempo el proceso y cómo me impactan las dos dimensiones, de tal forma que yo optimice, digamos, el tiempo de ciclo y el costo, pueden haber otras variables. Entonces eso es más o menos la temática de investigación que trabajamos en el laboratorio. Entonces, la primera parte va a ser una introducción de la universidad, de la Escuela de Minas, presentarse, el laboratorio donde hacemos investigación, qué temáticas estamos trabajando, y ver un caso puntual de lo que es la aplicación de optimización con estimación evolutiva, un caso ya puntual que se ha trabajado. Ellos tienen como unos 10 años trabajando la temática, son los que aplican esa temática que se utiliza mucho en la parte electrónica, tecnología, computación, electrónica, pero ellos lo aplican más en la parte de gestión, configuración de productos y procesos, aplicado, digamos, a esas herramientas. Entonces le damos la bienvenida a Paul Pitiot y vamos a iniciar con la charla. Muchas gracias por la participación. Entonces estamos para servirles.
So, thank you, Peter. My name is Pitiot.
Se me olvidó una consulta, lo vamos a trabajar en inglés, ¿verdad? No sé si no hay ningún problema ahí, cualquier, lo vamos a hacer seguido porque si no queda muy cortado. Entonces él solo habla, digamos, francés, inglés y un poquito español, él entiende, pero vamos a manejarlo en inglés.
Yes, because my Spanish will be approximately.
Poquito.
So, as we said, I will present you 4 parts. 3 first one will be short, with our research team for dispatch access month supervising, and after I will present the academic school, which is an engineering school where Luis made his PhD, and also the laboratory, and finally, in the main part, I will present my research work, with also research. My name is Dr. Pitiot. I'm married, still doctor. I'm graduate from General Mechanical and Production School named Eni Town. It's in the south of France. I will show you with a map on the previous next slide. I've made a specialization on industrial information, decision, and communication. That was a dual graduation with a master's degree in informatics, decisional, and automated systems. And after I made my PhD in the same school in industrial systems. And since 2010, I'm associate professor in computer science engineering school named Troisième Rodez. It's another small city near near Tarbes and Albi in southwest of France. I have a specific situation because I work in a small engineering school and there is no lab, so I make my teaching activity on this school, and for the research I join the École des Mines in Albi. It's just 1 hour from Rodez, and so in this activity that I supervise this in École des Mines. So on Troisième Rodez, my main activity is teaching algorithm and programming, different language, and also my engineering school has a specificity that all students are apprentices, and so main part, a great part of my activity also to follow up them in companies, and that's also have an incidence in my course because the way you have to teach is different. All the students are in company, so I try to have a specific course that prepares them to real life. And for the other part of my activity, so research, I'm associate researcher in École des Mines. My main topic, as we say, is combinatorial optimization algorithm and aiding decision tools. And also I made some additional course in metaheuristic, complex system conception, quality, and so on. So this is me. Just a little map to place every city. So there's Paris, Ottawa, Bordeaux, and I live in Rodez. There. After Louis and me work in École des Mines, so Louis is living in, when he is in France, he's living in Albi, and we work in École des Mines. And I also put Toulouse, which is the biggest city in this region, and is also well known for Airbus company. So we have a lot of research projects that are linked to a complex system, especially for the aircraft. So in my research part, I will show you some little examples who are aircraft. A more precise map, and you can see that I always be in this region because my engineering school was on top. It's in it. In the bottom. So just some pictures to show you Rodez, where I live. So here is my village. There is the map. And after this region is known for gastronomy, and this is the countryside. And we also have the biggest bridge in the world, 300 meters high bridge. So, and we have beautiful buildings, very old. So for Louis, living in Albi, he is lucky because I think it's the most beautiful, one of the most beautiful cities in France. It's UNESCO World Heritage with a cathedral and for the downtown. So it's really beautiful, but it's a small city. So for the other supervisor team for Louis, there is Michel Aldanando, which is the PhD director of Louis. He is full professor in École des Mines since a long time. He is also director of our research lab named CGI. He has a lot of activity. He is very well known in the community in France and in configuration community all over the world. So we have a lot of congress and conference with him. He is a reviewer for a lot of journal, project, conference. He has teach and supervise 30 PhD students and 60 master students. So his research interests are in design, configuration, and customization. For the same activity, he also had experience in designing tools for aiding decision system, especially interactive tools. For the scientific aspect, it's a knowledge-based system and constraint satisfaction problem. And also we take part of development and some specific tool we use, namely COFIAT and case-based reasoning. So that is for his research team interest. And after we have a lot of course designing experiments, statistical process control, like me, and from information system for production design, and so on, concurrent engineering. So he is the boss. And after we could find the last person for the team is Elise Varey, which is also operational supervisor like me for this. So she's specialized in constraint modeling and handling, and she has developed for his thesis the COFIAT tool that I will present in the research part. So she had the accreditation to supervise the research, and she had also supervised 6 PhD student supervising. She has the same topics for research than Michel, and my specificity is optimization algorithm, and they are specialized more on the subject of application subject. As we say, it's configuration and planification, and Elise is specialized for the case-based satisfaction constraint modeling and handling. So she has also course in development and project management and methods for product configuration and product design. So this is for our research team. So this is a mountain in our region. Here is a small presentation of the academy. It's the engineering school where we make our research. This is a very small presentation. So MINAPI is a part of a big group of engineering school in France, and it's very well known. It's also a part of University of Toulouse. And I will present in a few slides those entities. And for the research, we have a group of labs named Institut Carmon. So, let's say, Codemine is a part of Mines Telecom. It's a group of engineering school, a very big group and very well known. Which we have 10 schools in the group. And the other associate school, it corresponds to 32 students, including 9,000 engineering, and we have 1,700 PhD students. It corresponds to a great part of engineering graduated in France. It's 8%, and 25% of PhD students. So it's really a big group of engineering school. We also have a lot of researchers with a lot of contract with the industry, and generate a lot of activity within the research activity. So there is a lot of company created, and as I said, we also are a part of the University of Toulouse. So Toulouse is a big city near Abbé, and we are part of the University of Toulouse. So this university is one of the most old in Europe, was founded in the 12th century. And this is a very huge university with thousand students and a lot of professors and a lot of PhD school. The one where we study is one of them, and we have a lot of training students and researchers. The field of excellence are space and aeronautic, especially with Airbus. Also a lot of things, because all fields are covered by this huge university. So there is some key data with 650 engineering students in academy. So this is for the representation of the academy. So it's quite big in engineering school. There are no specificity. It's a generalist, non-specific formation. And after we have a free way to graduate, so they also have apprentice and regular student, and also we have some students in continuing education. There is more than 2,000 students graduate for each year, and 2,050 and 500 graduate since its creation. So it's one of the youngest schools in the group, but it's a nice place to study. We also have 4 applications in domain in master, so biotech engineering, eco-activity and energy, industrial engineering. That's the field we cover, and advanced material science and mechanical engineering. So a lot of possibility to interact. So with international dual degrees and 2 dual degrees from engineering and manager, and a lot of agreement to make pharmacist and engineer, and in fact, a master for research. So we students in PhD, you have to make a master for research. And the 5 master program for the French summer school, we made a lot of things for French students. You can come for summer and to study some specific domain. There is 5 of the academy. So it's advanced manufacturing process, and biomass waste for energy and material. Also pharmaceutical engineering, aerospace material design, manufacturing and innovation, and supply chain and lean management. So all those formations are very good, and you can come and have a nice day on Navi for studying this aspect with a very good professor. So here, this is also, we also have a free research lab, so 2 big ones, and 1 more smaller. And the 2 first one study, the first one is Rhapsody. It's a powder and process scientific domain. And the other is ICA-AB. It's the first 2 one are part of the National Research Agency. The ICA studying material and process for aeronautic and space. And we take part of the last one, the smaller, which is the name is CGI. It's in industrial engineering, and we are more specialized in improvement of enterprise company process as a multi-sectorial domain of application and crisis management. So we also have a lot of data for research in AVI. I think I will not show everything on this slide. But the main thing to know is we graduate a lot of students. We have a big staff, and we mainly work for the industrial of the region. So we have a lot of contracts, and we also generate patent and license to have applied research. So this is the goal. So after we graduate, around 80 students for each year. I will briefly present our lab and research team. The lab is named CGI, it's named Industrial Engineering Lab. We are 31 people, and half are PhD students, so it's a very small research entity with 2 computer scientists and 1 management assistant. We are 12 teacher researchers with 4 professors. The main concern are approaches. We propose approaches, model, method, and tools just to improve the value created for project and process. I will present this more next slide. So the goal is to propose the innovative product, process, and system. And we have some key competence in interoperability and new management. There is 2 teams in the lab. IO and Archive. Archive is the one we participate. So graphically, we have 4 key competence. The key competence are to act when there is numerous stakeholders for collaborative process. We also have competence in risk and uncertainty modeling, and also with the conflicting objective, so to manage when there is a different objective. And finally, our research, more specifically, on the product and process knowledge management. So all these competence allow to get models and tools to improve the value created in process or on project. So here is some example of projects we take part. So with every time industrial partner and PhD student. So we have no particular application sector. It's a generic research about modeling and editing tools. So we can find product medicine, you can find logistic activity, you can find our research team work on configuration, conception of aircraft, for example, with Airbus. We also have some researchers who work with a non-governmental organization for crisis management, humanitarian, or with the infrastructure of state. We also work for helicopter building and maintenance, or other projects in very varied field. Our goal is just to get some model created to treat some problem and generate corresponding editing tools just to improve companies that work on that problem. So as I say, we have two teams and 4 key competences. Our team is Archive for organization, risk, knowledge, and design. So we focus on decision support, making use of business-specific or expert knowledge for process or project development, and for process for product, system, and services. So here we handle different kind of model of knowledge, risk, uncertainty, and we study both product, system, and services, as well as project and process development. So just to have a good modelization and good tools. The other team is interoperability organization. They focus on development of approach and tools for various levels to support organization collaboration. But, that's not my field, so I cannot develop more this activity. Our team is specified. We have two sub-axes, as I said. It's risk management, and our axis is aiding decision and making through the use of knowledge, engineering knowledge. So we use. I will define more in the next slide what is what we call configuration, because it's a little bit different from design. So it's a routine design, and we also use some specific tools coming from. So this is for the scientific aspect. There is a constraint satisfaction problem that allow to handle model in an interactive way, and also for my part is a evolutionary approach that allow to optimize the search using multi-criteria solution approach. So for more information, you could find information on the website. It is in English, so you can find more information about the central activity and the different axes. The name of the author, if you want to come to make some study. So I will start the main presentation, the main part. It's our research, my research, and one quiz. So it concerns adding interactive configuration and planning, and we use constraint and evolutionary approach. So you can have a little overview. I will present the first work situation, and after there is two kind of tool we use. It's interactive configuration. That is a problem. We use constraint processing, and there is also, I will present after, the optimization issue, and I will try to show you some example, a small one, and after I will show you the results we had with some large problem and different approach we propose for this kind of problem. We conclude on my work and introduce Mr. Luis Garces Monge. Thesis. So, what is product configuration and project management? So, configuration is when you have to select product component or alternative. So, usually the user have to handle a software named configurator. He will enter his need for selecting a product. You can have an example of this kind of mechanic with, for example, for a car. You can go on the website of a car constructor and you can configure the car you want. So you select some components, and there is many study about this kind of problem in configuration. So it's a selection of components, and when you select component, the model, the tools, configurator have to keep integrity of the model. And for example, you have to propagate constraint. When you select some component, you have to directly select from the other components which are compatible or not. So there is many study about this kind of problem, which is adding product configuration, and among them you can find a constraint-based approach, the one we use. So I've put some references. After we have the planification problem, usually you first define a product, then after you use a planificator to know when you what could be the schedule of the production of this product, and you will know how much does it cost and when you could have your product. So, for example, on the car website, you can select the car, and once you select your car, after internal stakeholder can use a planificator to know when he can bring you your car. So this is another problem, and usually this is the sequential activity. So if you find that you want to car more volume, you have to come back to the first step of configuration and perhaps select another product to have your product in the plan. So this problem is really have a lot of studies, but interesting, like those I noted there, and there is a lot of study based on constraint-based approach. So our goal is to try to mix the two steps and to achieve configuration and planning in the single world. So it's a huge problem because you have a lot of combination in configuration and a lot of possibility in planning, and it corresponds to a search space very large. So we try to propose an approach, optimization approach to handle this, and we have some experimental results. So just to have a small explanation about the configuration. So this is the work of PhD work of Elizabeth. What we define is interactive configuration. It's when you have a set of components and you have a dialogue with the user, and the goal is to find a solution that meets customers' needs. So here is an example with origami. So for example, when you have some parts, some components, you can make a lot of different products with this. So for example, here with 7 pieces, you can have 6,000 combinations. So this represents a large search space, and it's just with 7 pieces. So in real application, you have a lot of not components, and the goal is to handle a selection of components and to have a good product and the product you need. So that's why you need a tool to make this step. So just to know what is the configuration. So the difference between conception and configuration, it's the routine design. So you have a need of the customer, and you have also you have a set of components. You also have the process to achieve the product, and the goal is to fit, and you know every configuration, possible configuration. So that's named the configuration problem. It's different from design, where you have a new product, new components, and or you don't know the process, here in configuration, we know the component, the need, and the process. So, and we check for every possible combination, so this is exhausted. So this is the configuration problem. We have a mathematical representation of this. So a constraint satisfaction problem is a triplet with a set of variables. This variable have domain, and you have constraint on the value of a variable between the different value of variable in the domain of this variable. So we define a solution of the constraint satisfaction problem as one set of value for every variable to reduce the domain to one combination of value, and this combination have all to respect the constraint. So this is a mathematical representation of this. So a solution is just a selection of value for every variable that respects the constraint. So to handle this, there is different approach. Ours is a filtering method. The filtering method uses some mathematical algorithm, which are arc consistency for discrete and mixed CSPs, and we also have 2B consistencies that allow to handle constraint and to select which value of which variable that respect the constraint. Another way to solve this problem, so we could have a filtering method. We also have solving method, which explore every possibility, and when you have a solution, you are sure that this solution is true and respect every constraint. So this is a good method, but it takes a long time with a big, with a large problem. It's not accurate to handle with interactivity the model. And also there is another kind of method named compilation map that compile before handling compilation map of the problem. So this is also a very performing algorithm, but it also corresponds to small problem. So as we want to handle a very large problem, we have chosen to develop a specific algorithm which is a filtering method. And this is the work of Optimización. So we developed a tool named Cofiat, which handles CSPs. So with different kind of variable, which are discrete. It can be discrete, numerical, mixed, or temporal. And also you could have variable which are conditional according to the set of value selected, which is named CSP conditional. So we applied this engine, this tool, to a lot of kind of project. For example, with Atlas for the aircraft conception, for the helicopter maintenance, for the building renovation, and a lot of things like that. We have used this model. So this model is named Cofiat, and it's a configurator which handle various algorithm to handle constraint and according to the nature of a variable. So it's a multi-interval, it's a piecewise constraint, and we have also an activation of constraint, arc consistency, 2B consistency, etc. So this is not my work. So just to introduce you to those concepts, but my work is optimization. So if we come back to our problem, we have something to handle CSP problem. So for example, for an aircraft, you could handle with Cofiat in the first step an aircraft model building interactivity. So the customer can select what he wants in the aircraft, the number of seats, the type of engine, for example. But he has some needs, but not for every decision in the model. The need he has in his mind, we name it non-negotiable requirement. So, for example, you want an aircraft with 10 seats, and you want to go to New York, from Paris to New York, for example. So you have some needs, but this needs does not fit every decision in the model. And usually, for the remaining decision, they are selected using default values. So this is one way, because those default values does not correspond to an optimal solution. So the idea of my work is to add a second step, which is use an optimization step, which is evolutionary algorithm. So I work on the second step. So here you can find an illustration. Before the first step, we have an initial solution space with every possible aircraft. The user enters his non-negotiable requirement. So after you reduce the number of possible solutions, and after we use our optimization algorithm to find the best compromise of the best solution. And those best solutions have to be a compromise because we have multiple criteria. For example, here we handle a model with the cost of the aircraft and the cycle time of the process. So we propose to the user a selection of the best solution that exists for this aircraft according to requirements we have on the first step. So this is the problem to solve. So to better illustrate this problem, I made a little example. So here you can have just two variables that for the aircraft, the number of seats, so it could be 4 or 6, and the range of the aircraft, be 600 or 900 kilometers, for example. This is the two variables for the product, which have two different values for each variable. You could also have a constraint that links those variables. For example, for a small number of seats, you could have a smaller aircraft, and you could have a specific range. After, you can add to this model the process. So here is configuration. Now we want to handle model with also configuration and planning. So here you can add different variables. For example, we have two tasks in the process to achieve this aircraft. The first task is sourcing the component, and the second task is assembling the component. And each task is represented by two variables. So the kind of resource you will use. So you can use a small or a slow or a fast resource for the sourcing, and you can also have a normal or quick resource for the assembly. And each resource corresponds a delay for the task. So it could be 2, 3, 4, or 6 for the sourcing, and also 4, 5, 6, or 7 for the assembly. So according to the product I select, and according to the resource selection, I will have a specific duration. And finally, also we have cost. So we have two objectives. The delay. So the delay will be the sum of duration of each task, and the product cost, and the cost for the product. So according selection of state of variable, the number of seats will cost 90, and if you select 6, it will be 120. And the same for the range, correspond to different size of the aircraft. So according to the product I select, I have a different cost. And also you have cost on the process side. So according to the resource I select, we have a different cost for the production of this aircraft. So the global cost is the summation of the product cost and the process cost. So here we have define configuration and planification problem for a small aircraft. And if we calculate every solution of this problem, so you can have you have two values for the two variables in product, and you have two values in the domain of the variable for resource selection in the process. So it leads to have 12 different solutions existing in the search space, and the goal of the optimization is to find the best compromise existing for this solution in the search space. Because you propose to the user those solutions, and you could select, okay, I want faster, and I could select more expensive solution, or I want less expensive solution, but I will have it with a duration more long. So this is a model pattern. In product, you have product variable, which have a constraint between them, and you also have product costs that are linked to the variable selected in the product variable. In process side, you also have process variable, which are selection of resource. Each task is linked to each other using precedence constraint. And you also have cost in process, which is the cost of the process corresponding to the resource selected. And finally, you have objective variable, which are the cycle time, which is the difference between the starting time of the first task and the ending time of the last task. And the total cost is the summation of product cost and process cost. This is a small model pattern, and this is working on more elaborated. So I show you with a very small example, but in our research we work on a more larger model. Here is the representation of the search space in a normal case. So you could see that there is a huge number of solutions, and there is also the initial problem, which are the blue point, and on our process we have the first step, which is interactive. So the user will select some option on the product and on the process, and it will reduce the problem. And the goal of the optimization approach is to find the best compromise for the cycle time and cost for the yellow point. Sorry, it's a zoom on yellow point, and the goal of the optimization is to find the best solution here with the triangle. So for talking about the optimization aspect, this is a very specific optimization problem. So we want to handle a concurrent optimization product and project. So we have criteria from product, which could be performance or product cost, and criteria from project, which are process cost and cycle time. So here for this study, we will select only product cost, process cost, and cycle time, but we could add more criteria like carbon or film like this. this is a specific field of optimization, which is multi-criteria optimization. We want to get not the best solution, but a set of the best solution. So it's called Pareto front. We have a lot of variables because we try to get the two aspects in a single shot. So we have variable from product and variable from process. So it's a huge subspace. Just for the product side, you have a very huge subspace. So when we test our model, we have a very big number of solutions. We also have a lot of constraints because we have constraints stemming from the product environment and from the process environment, and these constraints are not the same. In the process side, you have a precedence constraint and temporal constraint between the tasks. And in the product side, we have compatibility between different product components. So there is no existing, there is some kind of existing algorithm that we could use for this model, and we propose a new one, which is based on a evolutionary algorithm. So I will introduce later what is the evolutionary algorithm. Just to complete this description of the optimization problem, in this study we handle generic model of product, project, and coupling of the two environments. This is just one level of abstraction. So you have every variable describe the product and the process, and this is the first step of the study of the two aspects. And when you will have a solution, it will be refined by other algorithms. As the under model are for a very long time, we have unlimited capacity of resources, so we don't care about shared resource between activities, so we don't have it. And we also limit to two criteria model, so the global cost and the cycle time. So here is an example with the aircraft. So you can find on this example. Here you have the product configuration on the upper side. For example, you could have the seat number of the aircraft, the engine type. You also have the cruising speed and flight range. And those lines correspond to compatibility of the different values. For example, you cannot have the big aircraft, for example, with 10 or 12 seats, with a low power engine, and you must select the bigger aircraft with a high power engine. And also you could have a constraint between the cruising speed and flight range, because you have a capacity of the supplementary tank, etc. You could have, for example, a variable that describes the finition of the aircraft. So this is a first small example. And after the other side, you have the project planning. Here we have just defined 6 tasks, and for each task you have to select the quantity and the type of resource you will use for each task. So, for example, for this aircraft, you have the sourcing, you have the assembly, you have the potential activity if you need a supplementary tank. So this is the assembly of the tank. So you could have here and node or node. Here is the or node. So if you do not select here a supplementary tank, you do not need this activity, for example. and after you have a payment and delivery activity. So on this model, with the configurator, you could the customer could select which product you want, and the internal stakeholder can select which resource you will select, and to this selection correspond to the kind of product. And after optimization, but the customer and the internal stakeholder do not have choice for every variable. So the goal of the optimization is to take the remaining decision variable and to select which value is the best to get the best compromise between cost and cycle time. The decision variable are the input of the optimization process. So we define OCSP, optimization of configuration satisfaction problem, as a quadruplet. It's a VEC, like CSPs, and we add a new part, which is F, which is the fitness function, which allows to calculate what are the values of criteria according to selection of state of variable according to the state selected for the decision variable. So that will be used for the evolutionary algorithm. So just a few words about the evolutionary algorithm. So this is part of meta-heuristic. Meta-heuristic are part of artificial intelligence. We try to find a generic algorithm to solve problem. So in evolutionary algorithm, the goal is to inspire those algorithms are inspired by the evolutionary theory, made by Darwin. So it's a probabilistic algorithm based on the population of solution. The goal is to make some solution and to imitate the evolutionary theory. So it could be very performing. It could be used in a very large scale search case, because in reality it's used in infinite search case as our environment. Initially, those algorithms are made for unconstrained optimization problem. So the theory is the scheme theory. The goal is the aim is that if you have an individual with good skin, with good genes, they are usually more performing than the other. And if you combine the performing individuals, you will get an individual even more performing. So we will try to get the same kind of process within our optimization problem. So the first thing to do is to modelize what is the solution for our problem, and after we will build some individuals and evaluate those individuals, and after we will mix them to get new individuals and select the more performing to get a new generation. And generation after generation, those individuals will be more performing, and we will have an optimization entirely. This is a huge search case. There is more than 10,000 studies on this approach, and there is a lot of various approaches and studies. The goal in this kind of problem is here you generate an initial population, so you get some individual randomly, and generation after generation, the goal is to reach the best solution. So here is an illustration for one objective. Our goal is to get in multi-objective space. So usually this kind of algorithm is used when it's really time-consuming algorithm. So there is some specific case where you can use this kind of algorithm. It's when you have no exact approach for a problem. When it's a complex problem, or complex, I mean by the size, very big size, or complex objective function, or multi-objective. For example, for the decision aids, or the social behavioral, and for the very large scale problem. They are also accurate for relative or fuzzy objective function, like in monitoring system. If you have a small, if you have very small enough of time to find a solution, you can use it, but they are a little bit time consuming. Now we use a specific algorithm named SPEA2, proposed by Zitzler. Here is the main representation of the algorithm. So the first step is initialization, so you get some individual generated randomly. And after you have the genetical loop, the main loop. The different steps are, first you have to assign a fitness to each individual. In this study, the best individuals are selected and put in an archive to preserve them from the optimization process. So every generation, we kill all population, and we keep only the archive. So after a fitness assignment and archiving, you will select some parent for building the next generation of solution. So there is a step matching selection, which is the selection of the parents for the next generation. Once you get the parents, you will have to operate genetical operator to get a new individual, which are crossover. So for crossover, you can take more. Here for us, it's a couple of individual, but you can. There is a different approach to take more than a couple, but you take a couple of individuals, you mix them to get a couple of child of new solution. You also have a mutation which selects randomly some parents and randomly change their gene to get new individual. All those new individuals are named children, and you will look to the fitness assessment and so generation after generation, you will have more and more performing individuals because you select at each step the best performing individuals, then you mix them to get new individuals, and you continue until you reach the stopping criterion, which could be time or number of generation or performance of the set of the solution found. So there is some parameter to adjust on this method, which are the size of the population, the size of the archive, the number of generation or the other stopping criterion. You also have to set the probability crossover, which is the probability to select a parent to get a child by crossover. Also the mutation probability, and the mutation probability for muting one gene. So this is the parameter to set. It's a little bit difficult to set those parameters because it's you choose them by using your experience and according to the size of the problem and the particularity of the problem. And also you have a fitness function which depends on two facts. The first is the fitness function has to be you have one term that concerns the performance of an individual, and also the goal of the approach is to have the best performing individual, but also to make them to have a good repartition of those solutions on the Pareto front, because you want the most diversified set of solutions. So there is a term who corresponds to the density of solution, and another term to the performance of the solution. So this is the original, it was the original algorithm, but it can be used only on unconstrained problems. So we modify this algorithm to integrate the work of my Ellis Varig using constraint processing, just in order to get individuals that respect constraint of the problem. Because on the initial algorithm, you have no constraint. So here we have, on our problem, we have constraint. So we have to maintain consistency of the solution. So there is other kind of algorithm who do this job. I read some of them. Penalty function, the repair method. Penalty function is to add a penalty coefficient for the solution who does not respect the constraint. Repair method try to repair individuals that does not respect the constraint. And there is another kind of method named specific operator, and we are part of this family. Our proposition is to use the CSP filtering to print the search space and avoid inconsistent individual. So this is a little bit time-consuming process. So just a few slides to illustrate this process. So we have modified the initialization operator. So in initialization, the goal is to generate the individual, initial individual. So here we modify the initialization to take into account the constraint of the problem. Our operators for each individual generated, we have each time you select, you instantiate a gene or decision variable, you will filter the rest of the variable, the domain of the variable, to avoid inconsistent value. For example, here you have, for the small model, you have a representation of an individual. For example, you have the number of engine, the number of seat, the kind of finish, the resource used for task 1, the regulation for the engine, the file distance. So here are all our decision variables for in the model, and initially they have a domain, initial domain. So each time on normal initialization operator, you will select without taking into account constraints. So here, as we select randomly a first gen, we select randomly a value, and after we ask to the filtering engine to select from in the domain of other variable the corresponding value. For example, there was two value possible value for the file distance, but if you select the engine 1, you only could add 500 as a flying distance. So in this way, you couldn't have solution that does not respect constraint, because you check constraint each time you select a value. And so on, you select another decision variable, you randomly select a value, and after you filter the domain of the other variable. And at the end, when every variable is instantiated, you will have a solution. It's a random solution, but that respects constraint of the problem. So this is our initialization operator, and after we modify the initial mutation operator. In the same way, we check consistency of the operation. For example, you select in mutation, you select randomly one individual, and randomly you select a set of genes to change their value. For example, you select the second value and the fifth, and you uninstantiate those value, the value of those variables. So you will have the initial domain, and after we call the filtering engine, and it leaves only compatible values. And after you can select, for example, for the second value you select 4 randomly, and you filter the domain of the other variable, and after you will have a second mutation on the other gene, and you will have the mutated individual. So this individual also respects the constraints of the problem. And finally, we modify the crossover operator. So here, the aim is to get 2 individuals that respect the constraint. In the original approach, you exchange half of the gene of the individual. So the crossover operator is first to select 2 individuals in the matching pool, then to uniformly select the gene to cross, and after we made a differentiated crossover for each child. I've illustrated this by this slide. So we select randomly some gene numbers, and the first step is to select randomly which gene will be crossed. So we have the crossover flag. If it's 0, we do not exchange genes of parents, and if it's 1, we will exchange the gene of the parents. But the aim of our approach is to keep consistency of the child. So we will take the first gene. As crossover flag is 0, we will take the value of the gene of the parent 1. So this is for the child 1, this is 1, and for the child 2, it will be 2. And after, we filter the domain of the other variable. Here, there is no problem. After, as the crossover file is 1, we will select the gene of the parent 2. So here, for the child 1, it will have the value of the parent 2 for this gene, so 1. And after, we filter the domain of the other gene. And sometimes, you can have inconsistent value. For example, there is no more consistent value in the domain of the next gene. So we will add a mechanism, backtrack mechanism in the operator, and we will change the crossover file to get the value of the parent one. So this operator, and after so on, this operator will build individual by checking consistency, and we will take the part of gene of each parent, but we will select coherent combination of gene of each parent, and that will generate new individual that combine value of the two parents, checking by also checking their consistency. So we will have two consistent individuals. So we will test. We have tested this approach. We name the approach constraint filtering based evolutionary algorithm. First, to evaluate our approach, we compare it to an exact approach, which is branch and draw. We also evaluate according to against another possible approach, which is the performing approach, which is a feasibility rule based. That's another way to take into account the constraint of a problem using an evolutionary algorithm. So we code this evolutionary algorithm, branch and both, and we evaluate our algorithm on different kind of problem, on different sites. We also propose an optimization in 2 steps. So I will show you shortly after this process. So to evaluate this algorithm, you need to measure the performance of a set of solutions. So we use the Linear volume measure proposed by the same author as the evolutionary algorithm. It's measure the area domain by the set of solutions found by the algorithm. So we compute, we evaluate the different approach with hypervolume and computation time. So we made different scale of different size of model with a large model, and also we evaluate possibility of another process which is zoom with 3 different kind of model. So here is the result achieved with a small problem. I have shown you the aircraft problem, the small one. For this small problem, you can see on the curves the evolution of the hypervolume. So the goal is to get the highest hypervolume. So first, here is the result of a comparison between branch and bond, so the exact approach, and our evolutionary algorithm. So as you can see, the branch and bond, the advantage of the branch and bond is that when you stop, you are sure that you have the best solution. But with evolutionary algorithm, you are sure of nothing, because it's probabilistic approach. So you can see the set of solutions defined, but you have no guarantees that this is the optimal one. This is the problem with this probabilistic approach. So on a small set of problems, you can see that evolutionary algorithm find near optimal solution very faster, but evolutionary branch and bond can find also a solution. But this branch and bond cannot be used on a very large scale problem because it takes too much time. For example, here on the small problem, you have 47 million feasible solutions, and we reach a gap of 1.5% with the optimal value in half an hour. Here, in the horizontal axis, you have the time in seconds. So in half of an hour, you will get very good performance, while branch and bond will take a very long time to get this performance. But at the end, you have the best performance. So on the initial problem, we test 2 different kind of 2 different sizes on the small problem. So you can see that on the wall problem, the branch and bond is very long to start to find a good solution, while evolutionary algorithm increase very quickly, and in very large problem, branch and bond is not can be used. After we have a comparison between different level of constraints. So we made four models with low and high constrained model on the big side model, and also low and high constrained model on the smaller one. And here you can see the number of solutions and the constraint density of each model. On the small model without constraint, you have 6 million possible solutions. And when you take into account constraint, there is just 500,000 on low density and only 100,000 and a half for the high density. And on the full model, you have a very large 500,000 billion, 500 million of solution and 50 million real solution and taking into account density constraint in low density and only 12 million for the high density. So that corresponds to 4 models, 4 different sizes of model and 2 different levels of constraint. And as you can see on the small model, branch born could reach good solution, but on the large model, branch born, our algorithm finds very quickly good solution. And here it's just even the full model. It's a very small example with 12 decision variables. In the model we used to handle, industrial used to handle model at this step of the process around you have around 100 decision variables. So it will be very much big for the search list. So yeah, I can show you on the graph that the time need to reach the optimal value is increasing exponentially for the branch and born. So it cannot be used after 20 solutions, 20 decision variables. And our algorithm is proportional to the number of decision variables. So you can use it on very large scale problem. So we made a very large problem with 10 power 18 physical solution, very huge search space, and we have shown that we reach a very good solution in 3 hours and 99% of the optimal value in after 10 hours. So that gives us the idea that we could have an optimization in 2 steps. This is the last thing I want to show you. Here you can see the Pareto front, which after 24 hours of computation in a very large scale problem. And the Pareto front reach after 3 hours in the blue solution is the Pareto front reach after only 3 hours of computation. So that gives us the idea that we could launch the algorithm, and after a few time we could show the solution, the set of solutions to the customer, and he could select which area is interesting for him. So he could see this solution and say, okay, I just want a solution that total cost is lower than 500 and the cycle time that is lower also than 500. And you will launch again the optimization process on the reduced area. So for example here, you can say, okay, I want only the cheapest solution, the lowest time cycle time, etc. So we could have different zones, and we launch again the optimization process, but only on a part of the search list. And we have found that we could reach the same performance by 2 shots of 3 hours instead of 24 hours of computation. So here is the result. For the archive in blue, the blue solution has the final set of solution after 3 hours. the red one is after 24 hours of computation in a single shot, and we found that the triangle in green is the result achieved with only 12 hours of computation in 2 passes. But the second one is 9 hours only on a specific area of the search list. So we have shown, as those graphs show, that we could find best solution in 2 steps instead of one longer, but only by asking for the user on which area he is interested in. So for example, here is the 3 different areas, zone 1, zone 2, and zone 3. And on each zone, you can see that we find better solution in the 2-step approach than in a single shot without asking for anything to the user. So it's better for interactivity. So for example, in a real process, a man who wants an aircraft, you could launch, you could ask him to handle the configurator, and after you launch the optimization algorithm, you go to you give him a rendezvous for the next day, and after you will come and you will have the optimization result very precise with on a very large search space. So it can be used later. Well, here are the specific results. So in conclusion, my work, we can handle. We made a specific approach for a specific problem, which is product configuration and production planning. That can be considered and optimized simultaneously. We could have a specific, we use a specific evolutionary algorithm, and we develop this algorithm, and can do as well and better than other approach, especially feasible rule or exact approach, because it can deal with very large model and problem. We have proposed an original process with the Zoom in 2 steps of optimization, and we could now consider a very large model with 1,000 variables. The perspective for this work is to an hybridation with a local optimization algorithm, because the problem with the evolutionary algorithm is the time needed to reach an optimal value. There is a very quick increase in the beginning, but after you have a long time to get a precise optimization, and if you want the optimal value, you could wait for a long time. So you can make an hybridation with a local optimization algorithm to cut this long time. Also, we could use another meta heuristic than evolutionary algorithm. There is a lot of meta heuristic. And also, another thing we could make is because this is a routine design, so we could memorize solution from previous calculation and use it. So we can memorize an individual of previous optimization and use to speed up the optimization process, the new optimization process. And also, big need is that there is no real benchmark for this kind of problem, and we need one to correctly validate our approaches. And I put it, I underline it because it will be the research work of risk. Just to finish this presentation, here is this plan. we imagine 3 steps. Is on the first one. The first one is just to make this benchmark. So a benchmark is a set of models that represent the real problem in the industry. So you have to make a benchmark of this kind of configuration and planning optimization problem. After, we want to use this benchmark to improve our existing approach to consolidate our results. And third step, we hope we could propose and code and test new approaches and derivate from our approaches, and perhaps find a better solution. So for the work situation in the first point, we have made. So why did we make this job? Because there is no benchmark for the addressed problem. There is few benchmark on configuration and nothing in configuration plus planning. So we propose a generic model on configuration and planning process with some kind of generic model of modular product. Each module, the product is a composition of modules. Each module will be composed of various patterns, a group of variables that describe the part of the model. And we also propose a generic model of a process that corresponds to a sequence of operation. And we define the generic structure of an operation and propose various kinds of constraints that could be added to the model. For example, there is a possible model. We say a product is a set of modules. Each module is a set of patterns. You have to define for each thesis which kind of pattern could exist. For example, a pattern with some description variable and some family of components, and there is a different kind of link between those variables. And also there is different kind of constraint between this variable. So on the upper side you have the product with the list of products, and the lower side you have the list of operations. And those operations, we have defined the structure of link between variables of an operation with a type of resource, quantity of resource that corresponds to a workload. And also you have time variable with the ending time, the starting time, and the duration, which are linked by constraint. So this is an example of the generic model that we have to propose to the community. So this is its current work. And the work you have to achieve is to specify completely the generic model, to propose it to the community with the article and references. We have already proposed some articles to make a journal article. And once this generic model will be accepted and validated by the community, we will use it to generate a set of various models named benchmark. And this benchmark could be used by every researcher on the same problem to validate their approach. Thank you for your attention. Finish.
¿Hay alguna pregunta o duda?
The hypervolume is adjoining on the total cost and the cycle time.
The hypervolume is when you have a set of solutions, the optimization algorithm, the result is a set of solutions. The aim of the optimization is to obtain. The aim of the optimization is to obtain a set of solutions which are performing and diversified. So to calculate in one shot which set is the best one, you have to evaluate performance of solution and also diversity. So to get this this evaluation, we calculate the volume in the space dominated by the set of solutions. For example, here you have a set of solutions, and the volume it dominates is the volume of the space, which is on the lower part. So if you have a set of solutions with another solution here, for example, it will have a better hypervolume. And also, if you have a more diversified solution, it has a better hypervolume. So this is a very good measure because we can evaluate in the same time those two characteristics of the set of the solution, performance and the diversity. Okay.
Thanks a lot, Dr. Pitiot, for being here with us. I'm wondering what's your opinion about how complexity of the algorithm can increase if you break the assumption of unlimited capacity of the resources.
It will be huge.
Yeah.
Because
how can you approach that situation?
we does not approach it's very difficult, and on our problem that's not a problem, because this kind of tool appear in the first step of the study for a big system. When you buy, this is for the example, is for aircraft. When you buy an aircraft, you start negotiation 1 year before fabrication, at least.
Yeah.
At least. So we make the hypothesis, which is in fact is good, that you can adjust capacities of your resource during this year. So you can, if you are Airbus, you can build a new factory. You can employ more people and things like this. So we evacuate this one, because you cannot handle problem with such variable that you have in configuration, with planning also, with this constraint, because it's very hard.
Yeah. Thank you.
I have one question. I don't know if it is too basic, but I just gonna ask. Do you consider in your algorithm the interaction between the configuration values, maybe the interaction in another variable of performance? Because you made the example of selecting perhaps the type of engine will create a variable about flight distance. But what happens when the variable of flight distance depends on several values that interact?
You could have interaction between multi-variable. So you could have a constraint between. In fact, with Luis, we evaluate existing model, and there is never more than 4 variables implied in a single constraint. But you could have it. So it's in configuration, you only have compatibility constraint. So you have a set of value for each variable involved in a constraint, and you could have in reality no more than 4 value implied involved in a constraint. But you could have it. And after, in process, you never have such a number of combination enough of variable in the constraint. You could have one resource is not compatible with the use another resource, but you don't have no more than 2 variables involved. And after, there is also constraint between process and product. So here you can have at least 3 variables in the same constraint. For example, if you select some a specific material which could be dangerous, you couldn't have some activity in the process, but there is 1 or 2, at least 3 variables in the same constraint. No more than 4, and 4 it's in product. But you could have.
Otra pregunta. Bueno, muchas gracias por participar y venir. Muchas gracias también a Paul por colaborar con nosotros. Una gentileza de compartir el conocimiento de lo que estamos haciendo. Muchas gracias.
Thanks.